So we want to talk about accuracy versus precision. Accuracy is a measure of how close our measurement is to the accepted value. When you do a lab, you want your data to come as close to the accepted value of that variable that you're trying to find as you possibly can. Precision is a measure of how close a series of measurements are to one another. So if you're doing 3 trials, you want your measurements to be as precise to one another as possible, meaning you want all your measurements to be as close to one another as they can possibly be. When you think of these words, accurate means how correct you are. Precision means how consistent you are. Obviously, we always want to be consistently correct. We want to be both accurate and precise in our lab measurements, but sometimes we're more precise than we are accurate. And that's okay, because we'll be able to account for that then in our percent errors. If we look at a visual here of shooting a bow and arrow, if we shoot some arrows that aren't close to the bullseye and are kind of all over the target, we're going to say we're neither accurate nor precise. So if we had measurements that we wanted to get close to a specific measurement, let's say the bullseye area, and those measurements weren't close together, we would be neither accurate nor precise. If we shot all our arrows low of the bullseye, but they were all together, that would mean we're precise but not accurate. So we might have some values taken from the lab that are all close together, but they're not close to the value that we wanted. In order for something to be accurate and precise, we want to hit the target and have all of our trials very, very close together. You're going to be asked to calculate percent error in many of the labs that you do throughout the year. And a percent error is essentially a percentage of how far we are away from the accepted value. It's how accurate our measurements are. So you see the formula here for percent error. In the numerator, we have the experimental value minus the accepted value. Now the experimental value is what you find in the lab. That's what you get from doing your measurements. The accepted value is what you might look up off the periodic table or in your textbook or online. The numerator of this equation is an absolute value. You won't have a negative percent error. You take the absolute value of the difference between the experimental value and the accepted value divided by the accepted value times 100. And that gives you your percent error. Obviously, you always want your percent error to be a very low number. You want that to be as low as possible. Here's an example of a student who determines the density of a particular substance to be 1.40 grams per milliliter. If you want to find a percent error, given that the accepted value is 1.36 grams per milliliter, here is what we would do. We would just simply put in the 140 or the 1.40 for our experimental value minus the accepted value divided by the accepted value. And we're multiplying it by 100 to put it into percent form. So our answer would be close to 2.9%, which is a very low percent error. Please write this equation down someplace where you're going to be able to refer to it for the remainder of this year, because you will be using this calculation quite often to complete your lab reports. You're going to be calculating a number of derived properties throughout the year. And derived properties are properties that we cannot directly measure. For example, one of the first labs we do here is our density lab. And you cannot directly measure density. We don't have a density machine where you can put a substance in and it'll give you the density. You have to measure other properties in order to get an accurate reading on that derived property. So usually these are a combination of measurable units. And density, for example, is a combination of volume and mass. So we need to measure the volume of the substance in milliliters or cubic centimeters. And we need to measure the mass of the substance. Then we're going to be able to take those mass and volume readings and divide mass by volume to determine density. And you see the equation here for density is mass over volume. So this is what we call a derived unit. This equation for density is something that you should know. So here's an example of how we would use this density formula. In this case, you're given the object has a volume of 825 cubic centimeters, and they're giving you the density at 13.6 grams per cubic centimeter. We want to find its mass. So we want to find the number of grams. So what we're going to do is write down what we're given. We're given the volume and we're given the density, and we're asked to find mass. So since density is mass over volume, what we're going to do is rearrange that equation so we can determine the mass to be equal to density times volume. So we will multiply those two numbers together. Our units of cubic centimeters will be able to be canceled out. We'll be left in units of grams. And we have three significant figures in both measurements, so our final answer needs to have three significant figures. So our final answer for the mass is going to be 11,200 grams, or 11.2 kilograms. Another way to use density is to find the volume of a substance. So in this case, similar to the last question, we're given the density. However, this time we are given the mass of the liquid at 25 grams and asked to determine what the density is. So again, we're going to put down all the factors that we're given. We're given density and we're given mass. And given the equation for density, we're going to solve for V. So if we're going to solve for volume, we're going to take mass over density. We're going to put those numbers into the equation, and we only have two significant figures in each of our measurement. So our final answer should only have two significant figures at 29 milliliters.